In this lesson, we will examine a special type of sequence where the given formula is different from the formulas we have seen so far. Now to set this up, let's examine a sequence that we looked at earlier. In this example, we are given a formula that lets us calculate the value of any term in the sequence. So for example, if we want to find the value of term 10, we simply plug 10 into the formula and then evaluate this to see that term 10 equals 32. Similarly, to find the value of term 84, we plug 84 into the formula to see that term 84 equals 254. Now let's compare this example with this example. Here we are told that term 1 is 5, and we are given a formula for finding other terms in the sequence. Notice that our formula only applies to terms where n is greater than or equal to 2. The reason for this is that we already know the value of term 1, so we don't need a formula to calculate this term. To see why the definition of this sequence is different from the previous definition, let's take the formula for term n and use it to find the value of term 10. Here n equals 10, so we can plug 10 into the formula. At this point, when we simplify 10 minus 1, we get 9. So term 10 is equal to 3 times term 9 plus 1. But what is the value of term 9? Well, to find the value of term 9, we plug 9 into the formula. When we simplify this part, we get 8. So term 9 is equal to 3 times term 8 plus 1. But what is the value of term 8? Well, let's find out. As you can see, to find the value of any term, we must know the value of the term before it. When each term in a sequence is defined such that the value of each term depends on the value of the term or terms before it, we say that the definition is recursive. So in this example, if we want to find the value of term 10, we must go to the beginning of the sequence and calculate every term up to term 10. So let's take the formula here and use it to find the value of term 2, since we already know the value of term 1. When we plug 2 in for n and then simplify, we see that term 2 is equal to 3 times term 1 plus 1. Well, we already know that term 1 equals 5, so we can add this to our calculations. Now when we evaluate the right-hand side, we see that term 2 is equal to 16. Next, to find term 3, we will take the formula and plug 3 in for n. When we simplify this, we see that term 3 equals 3 times term 2 plus 1. Well, we just determined that term 2 is equal to 16, so we can add this to our calculations. Now, when we evaluate the right-hand side, we see that term 3 is equal to 49. To find term 4, we plug 4 in for n and simplify. We just determined that term 3 is equal to 49, so when we add this to our calculations and then simplify, we see that term 4 is equal to 148. Of course, we could continue this process indefinitely, but this is enough to list the first 4 terms of the sequence. Okay, now let's examine another question. Here we are given the values of term 0 and term 1, and we are given a formula for finding subsequent terms. Our goal here is to find the value of term 4. To do this, we must begin finding the values of terms at the beginning of the sequence. Since we already know the values of term 0 and term 1, let's find the value of term 2. When we plug 2 in for n and then simplify, we see that term 2 is equal to 4 times term 1 minus 2 times term 0. Well, we are told that term 1 equals 3, so we can add that here. We are also told that term 0 equals 6, so we can add that here. When we simplify this, we see that term 2 is equal to 0. Now on to term 3. Here, when we plug 3 in for n and then simplify, we get the following. We just determined that term 2 is equal to 0, and we know that term 1 is equal to 3. When we simplify this, we see that term 3 is equal to negative 6. Finally, to find the value of term 4, we plug 4 in for n and then simplify to get the following. We now know that term 3 equals negative 6, and we know that term 2 equals 0. When we simplify this, we see that term 4 is equal to negative 24, so this is the answer to our question. Okay, let's summarize. In this lesson, we learned that recursive definitions of sequences typically require us to start at the beginning of the sequence to find the value of each term. In this lesson, we will examine the sums of sequences. This means we'll take sequences, such as this one, and find the sum of its terms. These sums are referred to as series, but you don't need to know that for the test. It's also important to know that the sums you encounter on the GRE will not necessarily be expressed as sequences, but the techniques you will learn in this lesson can be applied to find those sums. Alright, let's begin. When it comes to finding the sums of most sequences, you will need to know two important formulas. I will introduce the first formula through the following story, which may differ slightly from the historical account. The story is as follows. In the 18th century, there was a boy named Carl Friedrich Gauss who would later grow up to be a great mathematician. One day, when young Carl was misbehaving in primary school, his teacher tried to punish him by making him add the numbers from 1 to 100. As the story goes, the young boy produced the answer within seconds. The manner in which he produced the answer is as follows. First, recognize that adding the numbers from 1 to 100 is the same as adding the numbers from 100 to 1. Also recognize that if we add both sets of numbers here, we are adding each number twice, so if we add all of these numbers, we must take the sum and divide it by 2 to get the sum of the numbers from 1 to 100. Now, while it seems like more work to add each of these numbers twice, Carl noticed that a nice pattern emerges if we add the numbers in certain pairs. First, when we add 1 and 100, we get 101. Next, when we add 2 and 99, we get 101. When we add 3 and 98, we get 101, and so on. At this point, all we need to do is find the sum of all of these 101s. To do this, we need to know how many 101s there are. Well, since we began with the sum of 100 numbers, there must be 100 pairs of numbers, which means there must be 100 101s. So to find this sum, we simply multiply 100 by 101. Now don't forget that this sum represents the sum of both sets of numbers here. So to find the sum of numbers from 1 to 100, we must take this amount and divide it by 2. When we evaluate this, we get 5050. Now if we generalize these results, we can say that the sum of integers from 1 to n will equal n times n plus 1 divided by 2. So for example, we can use this formula to find the sum of numbers from 1 to 39. Here n is equal to 39, the last number, so the sum of the integers from 1 to 39 will equal 39 times 39 plus 1, all divided by 2. We can simplify this as follows, and at this point we can simplify 40 over 2 to be 20. 39 times 20 equals 780, so the sum of the numbers from 1 to 39 is 780. This formula and the technique used to derive it will help you solve several questions involving the sums of sequences. Now the second formula we will examine can be derived from the answer to the following question. We want to know how many integers there are from 12 to 47 inclusive. In other words, we want to know how many integers there are from 12 to 47 if we include both 12 and 47. Now a common mistake here is to subtract 12 from 47 to get 35. To see why this approach does not work, consider a similar question. How many integers are there from 5 to 8 inclusive? Well, if we apply the same approach and subtract 5 from 8, we get 3 integers. But when we list the numbers, we can see that there are 4 integers. Now the formula that applies here goes like this. The number of integers from x to y inclusive equals y minus x plus 1. So for the question shown here, the number of integers from 12 to 47 equals 47 minus 12 plus 1, which equals 36. Okay, let's summarize. In this lesson, we learned the formula for finding the sum of integers from 1 to n, And we learned the formula for finding the number of integers from x to y inclusive.